I'm Andy Nichols. I am a software engineer at the Qt company, previously known as Digia. I'm one of the embedded developers. My passion is embedded Linux. So that's what I'll talk to you today about. Today's topic is device creation with Qt Enterprise Embedded. So I'll quickly give you an overview of the things we'll talk about today. The first thing is I want to establish what the problem is. What are the challenges of device creation? Then, of course, I will talk about the solution that we propose, and that is Qt Enterprise Embedded. And then we can actually delve into the usage of Enterprise Embedded, first starting with the prototyping phase, what you actually need to do to get something up and running and developing. And then we'll move into the device creation. This is the actual productization, taking custom hardware and making it run the thing you prototyped. All right, so let's just go ahead and get started. So, first topic, the challenges of device creation. I think this image sums it up quite well. It's all about doing it yourself. You're the one in charge. The first thing is that you have to realize with device creation that the application is just one step. With the other Qt on other platforms, generally everything else is taken care of taken care of for you. You just have to create the app, deploy the app, publish the app, and that's hard enough in its own. But it's just one thing to consider. Qt solves this problem by providing the application API. It makes it easy to write apps across platforms, but it's just the app. The second thing with device creation is that it involves hardware, and the needs of your application actually dictate what kind of hardware you're going to need to run your Qt application on. So a couple of examples here. First, we have this ebook reader. If you want to run an ebook reader, the application itself there isn't very demanding, and I mean, yes, you're rendering text, but you don't actually need to be animating constantly. You can actually just render something once, put it on the screen, and there it can make sense to have a lower end CPU, GPU, and have an e-ink screen. The second case I have here is a smart TV. In this case, everything's very multimedia driven, so you're going to need more powerful hardware to facilitate the decoding and display of video, maybe complex animations, maybe even apps from custom providers. So the actual application can define what kind of hardware you need to run on. And then another thing to consider is that both the application and the hardware will dictate what kind of operating system you'll actually need to run. In some cases, you have hardware that needs a custom kernel, things like that. So you can run Linux, you can compile it, you can write the drivers yourself, you can do all the things you need. Use Linux. In other cases, maybe the drivers only exist for Android. The BSP provider actually only provided graphics drivers for Android, so you're kind of tied to, if you need OpenGL support, you need to use Android. Or in some cases, your application has hard real-time requirements, in which case you'd have to select an OS that can actually provide those real-time guarantees. The next thing is that it's up to you to provide the SDK. For the mobile platforms, or like the desktop and the mobile platform, this is actually provided for you. You think you're downloading a Visual Studio, now you get a tool chain, you have the Windows SDK, all that's there already. Same thing with Xcode, you download that, you already have all of the tools you need to develop the app. If you're creating your own device, you have to provide the tooling. You have to provide a tool chain to actually generate binaries for the hardware. In many cases, it's a cross-compilation tool chain where it has to be capable of running on your desktop machine, but generating code for whatever your target device is. It's your responsibility to actually provide a system image. This is the code that actually runs on the device, what you're going to, like the OS plus the tools plus the apps, everything you need to actually bring up the device. And then you have to provide a sysroot This is what actually provides all of the development headers, the include files, the shared object files that you can actually link against the things that, basically it's the development files that will represent the things that are in your target image you flash to the device. And so Qt fulfills the need to actually abstract away the operating system and the hardware. So that's good. It makes embedded development easier, but it's not everything. Qt can only get you so far in itself because you still have to provide the platform to actually develop on. You have to provide the toolchain, the hardware, the sysroot, all of these things. So that's where we have our solution, which we're calling Qt Enterprise Embedded. And this actually consists of three main things: the Qt, the platform, and the tooling. So to start with, Qt itself, which most of you should be familiar with, that's included in this. This would be the most up-to-date, or the current release of Qt, so whatever the latest Qt release is. In this particular instance, this is Qt 5.3.2, soon to be Qt 5.4.0. And in addition to that, we have several of these additional tools that make sense for device creators to use when creating their applications. So this is the list. I'm going to go into a bit of a detail with each one. The first one, very useful in the device creation space, something you may overlook if you have a device with a touchscreen but no hardware keyboard, is that you'll have to develop, if you need to actually do text input, a virtual keyboard. And in many cases, this is more complicated than simply implementing a keyboard, because then if you want to deploy something to, say, a non-Latin typeface country, you need input methods. So maybe you want, if you're deploying in Asia, you want to have like pinyin text input, so you're typing the actual syllable that you're saying and then selecting which character actually represents that. And so you're going to need a virtual keyboard for this. So we provide an API for this. I have a couple of screenshots here of the virtual keyboard in action. It have the just regular text input, Latin characters. It has suggestions. So actually, if you're typing something, it's suggesting words that you might, so you can have text completion of Arabic. And then this keyboard's also stylable. Everything about it can be changed. There's a very powerful styling API. Next thing is the Qt Enterprise or Qt Quick controls. These are actually just additional Qt Quick controls that make sense in the device creation space. Maybe if you're implementing a HMI, or in this case a dashboard, you can see this radial gauge here, have a pie menu, linear gauges, dials. So lots of additional controls. One of the other things that you might overlook is if you're actually implementing the hardware, your application generally is going to be the only application running on the device. So if you need to do things like configure Wi-Fi, it's actually up to you to create that user interface as well to configure the Wi-Fi. So if there's a protected network, you'd have to be able to select the network, what password it is, connect it, turn the Wi-Fi on, like the antenna on itself. So we actually provide an API for that to help you out there. And this is the Wi-Fi selection utility from our demo launcher that's provided with Qt Enterprise Embedded. We also have a charts and 3D data visualization API. In your UI, it might make sense to either have a 2D visualization or even a 3D visualization if you actually have the hardware capabilities. You actually have a GPU on your embedded device. You can do that with these APIs. And we also have the top-tier support for Qt Web Engine. The first release of Qt Web Engine, the 0.9, was actually target at embedded Linux and embedded Android. So we actually have that working already in the current release, very well supported. Here I'm actually running this is a Nexus for an Android device, and or embedded Android in this case. And I'm actually running Enterprise Embedded on this and running WebGL on that hardware with the Web Engine browser. And that, I guess that's a good overview of a lot of the additional tools for device creators. We also, I didn't have a slide for it, but we also have support for the Qt compiler, which really makes sense in the embedded space. Okay, so now that we've talked about the Qt portion of Qt Enterprise Embedded, the next thing is the platform, and this is one of the pieces, the big pieces that was missing before when you're just using Qt on there. So we actually provide a platform for you to develop off of. So right now we actually have two choices for platforms. We have what we're calling embedded Android and embedded Linux. So embedded Android is, for all intents and purposes, Android. And for the most part, it's the exact same Android stack that your phone runs. What we've done instead for the embedded Android stack is actually removed any services that use Dalvik, disabled them in the services, the init.rc file, and instead Qt then becomes the middleware layer. So we can use all of the Android graphics drivers, the Android kernel, all of these things, everything in the Android user space that doesn't use Dalvik, but run Qt on top of that. So this enables you to do this. Decreases the memory footprint of Android in general, and it also increases, or it speeds up the boot time with just a standard Android device. The second thing, or the second platform, is embedded Linux. This is the standard embedded Linux you think of, running the Linux kernel, and then we have a Linux distro that we've defined, a bare bones Linux distro that defines all of the things necessary to use the features available in Qt 5 for embedded Linux. And then Qt, again, is your middleware layer that you develop applications on top of. So as we go into a little bit more detail about each of these platforms, the embedded Linux platform, here we're actually using the Yocto project tooling to generate this, this base layer project. We provide a boot to Qt meta layer. These stacks are, I guess if you're not familiar with the boot to Qt terminology, our stacks are called the boot to Qt stack, software stack. And so we provide a boot to Qt layer that you can actually inherit in your Yocto build script that will provide the packages and distro you need to generate your base layer image. Yocto, if you're not familiar, is the industry standard for these embedded Linux tool chains and the tooling around generating these tool chains and SDKs. In addition to this, there are many different like meta layers available. Yocto distributions are actually built off of combining various meta layers together and then generating a final product. An example of this is that if you were going to run on some Freescale hardware, Freescale actually provides a couple of meta layers that provides that actually has their BSPs. So you can pull down a Linux kernel that has the patches needed for running on different types of Freescale hardware. You can have, if you're running, say, the IMX6, you can have the graphics SDK installed. And all of this stuff, basically, on the Yocto side, you say, inherit the Linux kernel, inherit OpenGL, and it will automatically pull the things you need when you're building the SDK. So you're able to actually mix and match various meta layers to meet the needs of your project. On the embedded Android side, we do what we would like to refer to as Android injection. So rather than building up a full stack using the Android open source project, we can actually take existing Android devices, maybe just your phone, and convert that into a boot to Qt image. So change the services that are actually booted up, inject the Qt middleware layer onto that, and then that device then becomes a boot to Qt device that you can use for your own purposes. You can think of this, this might work better in the smaller volume space where You find a tablet that actually meets your needs already, but you want to use it for custom needs. You can actually take this alone and turn that into your device. Again, this is Android without Java, so we're using the platform developer APIs instead of the Android application developer APIs. And then, like I said, take an existing device and make it fit your needs. So that's the platform choices. If we move on to the actual tooling involved with Qt Enterprise Embedded. Again, if you go back and look at what is available on other platforms. So if we're dealing with mobile, for Windows Phone, you're going to install Visual Studio. For iOS, you're going to install Xcode, and for Android, you're going to install the Android SDK. And in these cases, they all provide IDE options, and it's really, I open up that IDE, I hook up my device, and I can run things directly from that. And you in the device creation space, you have to mix and match a solution to actually find that in many cases, whether that be in Visual Studio or Eclipse, or just find something that will actually allow you to work visually on your device. Well, in Qt Enterprise Embedded, we do that through our Qt Creator IDE. No surprise, we choose this IDE. How many of you have actually used or currently using Qt Creator? Awesome. So we're actually providing that, and all of the tooling we have around Enterprise Embedded is also working through Qt Creator on Linux. So in addition to providing the IDE, we actually provide predetermined or pre-configured kits, or everything in Creator revolves around kits anyway. So even in the mobile space, if you're developing mobile apps for Qt Creator, you just select the iOS kit or the Android ARMv7 kit, and you're able to deploy the device. Well, we make that just as simple on Embedded now. So whenever you either download one of our reference images or create your own, what you get is a kit that's installed in Qt Creator that already has all of the things set up you need to build for your device, debug on your device, profile on your device. Everything's already there, ready to go, just talking to your device over USB or Ethernet. And speaking of USB and Ethernet, we're also a big fan of this one-click deploy. So being able to hook your phone up to your computer, the IDE sees it, and then you can deploy to it. Well, we also have achieved that with Qt Enterprise Embedded through Qt Creator. And this is actually capable right now over both USB, like directly connecting, say, if your device supports USB host, you can hook it up to the thing, we'll recognize it, and you can deploy to it. And if you don't have USB host support, you can use, you can connect over Ethernet as well. So we actually support remote debugging as well. So being able to, run your application, build your application from Qt Creator, just hit play, and then you can actually run a GDB server on the device, connect to that, and then step through your application, the C++ code of your application, line by line from your host computer, and then be running on your device. Same thing with QML. If you want to either step through or see the live code running on the QML, you can do that as well in the same way that you could do for the other platforms or natively. We also provide the capability to do remote profiling. Right now, that's only for QML, but we intend to do the C++ side of this in the future. So you can see here, this is the QML profiler actually running, or the analysis that it actually ran on the device. The neat thing about this is it's actually still running full speed on the device, so it doesn't actually compromise performance to get this data. And then if you don't actually have access to the hardware, or you don't have enough hardware, we provide a device emulator to simulate the actual embedded Linux or embedded Android environment. Here we have the emulator running, showing the Enterprise Embedded demo launcher. This is the application that will boot up by default, just to give a demonstration of how you can expect the performance and the various features on a given piece of hardware. All right, so I guess that establishes what Qt Enterprise Embedded actually is and all of the things it encompasses. Now I want to talk a little bit about the actual usage. So first thing is the prototyping. This is the first phase of device development. You want to be able to show something off immediately. So we facilitate this by providing reference hardware. So actually selecting some easily or commonly available hardware that you all can obtain that also represents the same kind of system on chips and hardware that you will likely eventually make your final product based on. So with this, we actually intend, or we do provide pre-built images that you can flash to these devices, whether that be directly onto the device's internal memory or through an SD card. And you could also, we provide an SDK that is intended to build for this device. And the idea being that we want you to be able to start prototyping from day one with when you get this stuff installed and have your hardware. So for each platform, we actually have a different set of reference hardware. So for Linux, we provide reference images for the BeagleBone Black. This is the Texas Instruments device with the Satara chip. We have the very popular Raspberry Pi board. This is a Broadcom chip, and it's very popular for hobbyists, very commonly available. It has a pretty nice GPU for a device, but not so great in the CPU department. We have, of course, the emulator that will come, that you can use without any hardware itself and can be installed by default with the Qt installer. And then we have the IMX6-based devices. IMX6 is a system on chip. If you were at the keynotes earlier, there was a lot of discussion about this. This is actually a great piece of a great SoC for Qt. We run very well on it, and our reference devices really reflects that. So we have three IMX6-based boards for Linux. We have the Tordex Apollos. This is the module type board where you have a carrier and you install a module on it that you can switch out. We have the Freescale Sabre board. This is the Freescale's demonstration board. Several people out there are actually showing these devices. This is like a tablet that's been stretched out in various layers. And then we have the Nitrogen 6X from Boundary Devices. This is another IMX6-based device. For embedded Android, we have support for the two Nexus 7s, the 2012 and the 2013 editions. We have support for the BeagleBone Black and the two IMX6 devices from the previous slide, and then, of course, the emulator. Okay, so now that you kind of know this, like what to expect, here's how you actually get it. So if you want to get started, it's as simple as installing the SDK, like actually going into the Qt Enterprise Embedded or the Qt installer. If you have this evaluation or this license enabled, then you'd be given a selection of what platform do I want to build for? Do I want to build for embedded Android, embedded Linux? And then it gives a list of actual reference devices. You just check those off. It installs the images and SDKs onto your computer. And then it's just a matter of running the deploy scripts for each one of those reference devices, which will either flash the device or the SD card, and then hook up your USB cable. And as long as you have the right kit selected in Qt Creator, then you should be able to deploy to that reference device. And the benefits of actually prototyping on hardware, I think it might seem clear, but it's worth mentioning that it's good to be able to test the various SoCs, the system on chips, and see if it's a good fit for your product. If the demands of your product are such that or the application you actually intend to make are that you don't really need a whole lot of GPU support, but you need a lot of CPU support, maybe this Satara chip would be a better fit for your particular device, and so you can just look at it and see, like, this SoC works pretty good for what I intend to do, and this can influence your purchasing decision in when you're creating the actual hardware. You also should be able to fairly easily mock up your application or your device in general. So you can either show your boss to get the green light to go ahead with the project, or if you're trying to get venture capital, like actually having something there, like saying, look what we have, we're running already. This should help out quite a bit. And of course, since we're using Qt, any of the code that you do for your prototype, you'll be able to use in the actual end product. So now I want to move to the actual device creation phase. This is if at this point, it's really easy to just take some reference hardware and get started developing. But it's a little bit less clear. How do I go from prototype to device that I had made that includes this SoC and only one serial port and maybe Bluetooth built into the board? How do I go from a reference image to actually do that? So I'll talk a bit about that and how to do that on each platform. So we'll delve into the Linux Device SDK first. So the way that this works, if you're going to build a custom SDK and image for a just arbitrary Linux device, one that's not a reference image, the first thing you need to know is that it takes place in 3 stages, the actual creation of this. So the first is that we will use Yocto to generate a base system image and an SDK. And this is where we build this base system image that contains all of the things necessary to build Qt 5 and the SDK to actually do this. Then we take that Yocto SDK and we run another script outside of Yocto that actually generates and builds Qt, the add-ons or the extra add-ons I mentioned earlier, and any of the utilities that we use in the boot to Qt stack. And then that gets combined with the base system image to become the final image that you'll actually use from Qt Creator and flash to the device. So you'll get yet another SDK and image. And then the third stage, the simplest stage, is just registering the SDK with Qt Creator. It's a very simple script. I'll show you one line step, and then everything just works inside of Qt Creator. So first off, using Yocto. This is something that you will, if you're in the device creation or going to get into the device creation space with embedded Linux, you'll have to become very familiar with, because you'll spend a lot of your time doing the board bring up, modifying the Yocto scripts. So again, we create a base image in Yocto, and we do that by building up these vendor specific meta layers. So if you did have a custom piece of hardware, hopefully the vendor that you're actually buying the hardware from, or like providing the hardware, has Yocto support and will provide these specific vendor specific meta layers. Like the previous example with Freescale, if you have a Freescale chip, you should be able to pull in the Freescale meta layers and actually have it generate the kernel, or provide you a base kernel to modify, and then the graphics drivers and any other like multimedia utilities, hardware debugging or hardware decoding of video streams through GStreamer, things like that, provided that work on that hardware. And you can actually take that and customize that. So one of the common use cases there is that you'll need to modify the kernel for your hardware. So if your hardware has, you need NFC support, then you'll have to add a kernel module to actually enable you to talk to those NFC devices. And following that line of thought with the NFC, you would also have to enable or make sure that the stack contains the I think it's the near daemon. Make sure that gets built and included in the system image. Any other features or third-party libraries? This is where you'd also add. I'm mentioning the near thing. If you want any additional tools in your stack or additional libraries, maybe your app requires Boost. This is where you would add Boost to the SDK here, so that you'll have it later in your toolchain or in your sysroot and toolchain. So what we provide you is what we call the build your own stack scripts. And this is pulled directly from our documentation, an example of how you'd actually do this. So the first thing you'd have to do is actually set up your Yocto toolchain, like actually pull down all of the prerequisite meta layers. And so we provide an easy script to actually do this. This boot to Qt init build environment. If you run this script, it will actually go ahead and download each one of the things you need to get started. And then from there, it's just a matter of setting those two environment variables, this template comp and machine. Template comp actually points to a template that we have that will generate the Yocto-specific configurations for building our distro and pulling down the layers, or making sure that it's associated with the layers that you need. And the machine variable actually defines what piece of hardware you're building for. The example I use here is the BeagleBone. And this is actually reflected in these machine configurations in Yocto that define, like, oh, this is using, it's an ARM v7, it has this SoC, and fortunately, most of the time, these are provided by the hardware vendors of the closest thing you're actually building to. But it's fairly straightforward to modify these for custom hardware as well. And then once you've set that, it's just a matter of running this open embedded init build environment, and then the build folder, in this case, build BeagleBone, and it will set up the entire environment that you need to run the next two lines, which is the bitbake. You run the bitbake utility. First off, you build the boot to Qt embedded image. That builds the distro, builds the image that you would flash to the device, and then it builds the SDK, which will contain the actual toolchain and sysroot. Okay, and I expect that since you'll have to become so familiar with Yocto, well, I guess I should ask, how many of you actually used Yocto before? That's expected. So you'll have to know how to use it fairly well because you'll be editing it in general. So, of course, the best resource here is the Yocto user manual. It really provides all of the details. The problem is that it's also not for beginners, and it is definitely a very detailed document. So I actually recommend this Yocto ebook, this embedded Linux development with Yocto project. We'll say if you read this book as a beginner, you'll be able to read the Yocto user manual. This will put things in perspective and actually make it possible for you to take it the rest of the way by looking up things in the Yocto user manual. And of course, if you're not into doing board bring up and all of these things, the nitty gritty of the base layer image, then of course the Qt company and its partners, we all offer services to help with this process. Okay, so that covers the first phase of the development. That's just the base SDK. After that point, you actually need to build Qt and the add-ons. And we also provide scripts to do this. So here just shows the basics of this. First off, you init the build environment for the particular device you're building for. In this case, we're building for the BeagleBone. What this will do is make sure that you have all of the source code you need to build Qt and the add-ons, so pulling it from the right places. And then it's just a matter of running these three scripts: the build Qt first, build the extras, build the image. But all of the magic here is actually in the scripts itself are the magic, but the configuration is the thing that you'll have to worry about, the only thing you need to change. And that actually covers 3 different files. So if you can create these 3 different files, then you'll be able to build everything and have it set up to run in Qt Creator. So I'll go over quickly how these 3 files work, or what they actually should look like. So the first is actually defining the device you're building for. If you're familiar with cross-compiling Qt for a device, this might seem familiar because we're actually defining the customizations to the make spec. So we're building for embedded Linux, the machine is BeagleBone, and the device is this Linux BeagleBone G++, which is a device make spec. And then, like you can see here, it basically is saying that the sysroot, it looks for the sysroot in the correct directory and uses the correct compiler. AppController.conf is the actual definition of what environment variables you want to use by default when you're running your application on the device. This, you can see here, we're actually defining the virtual keyboard because the virtual keyboard needs to be loaded as an input method. But other things that you might want to add here is that if your device has a touch screen and it needs special consideration of making sure that it's actually this input device, then you would define that here as well to make sure that you have touch support. And then the Qt.conf for the machine, this actually defines the location of your sysroot. That's generally going to be exactly the same as it is here, changing the actual name of your sysroot folder in your toolchain. And it seems a bit complicated, but it's really, most of that is exactly the same, as each one of those devices has roughly the same configuration on this side. And then once you've done that, it should build everything once again. It'll take the base layer image and combine it with the Qt middleware layer and the tools, and you'll have a new SDK and a new image, and that's the thing that you actually will flash to your device, which we also provide the deploy scripts to do that. And after you've done that, it's just a matter of the folder that you built all that stuff in. If you run this one line of code, this setup Qt creator, it will actually set up the kits for you in Creator, and they'll just show up as in the same way that any of the reference devices do. Yeah. So I guess I can I'll go ahead and discuss briefly the Android Device SDK. So this actually works slightly different, because rather than building everything from scratch, including Qt, we actually will support any Android device that meets these three requirements. So right now we provide packages for both Android 4.2 and Android 4.4, and as long as you have a device you can get root access to and a way to actually access the bootloader, then you should be able to modify the device. So the basics of Android injection is really two steps. So the first is to modify the init.rc file. This file actually defines what services are started up on your Android device at boot time. And then we deploy a few payloads to the Android device based on the version. So for an Android 4.2 device, what we do is just deploy the system and data partition of folders to the device, and then modify the init.rc with a sed script we actually provide to turn that device into a boot to Qt device. And I won't go over all the details of this, but taking just a standard Nexus 4 phone, this is my old phone before I upgraded, turning this Android device into a boot to Qt device, I can do the same development with everything on. It was just a matter of doing these things. It's a bit tricky with this device because everything's in Flash. There isn't an SD card I can put things into, so I can't just put it into my machine and modify things. I have to actually pull down the boot partition of this thing, the boot.img, and then extract that out, and that's where the init.rc file lives. And extract that out using various tools, modify the init.rc, pack that back up, flash it to the device, and then deploy the payloads, which also can be a bit tricky because we're actually having to use ADB, but it's still doable, basically flashing the data and system payloads to the device. And once that's actually done, it's really a matter of rebooting the device. And I'm going to go ahead and boot up this device here. It might be a little bit hard to see in the back, but it is just a standard Android device, except instead of taking quite a significant time to boot, within 10 seconds, I have the boot to Qt reference image here running. And of course, it has all of the little neat features that come with it. And so we'll actually play with that a little bit. So let's do some development for this device. So I just need to switch the desktop mode. And here, let's zoom in a little bit. So we have a Qt creator here. And I have a simple application that I wrote earlier. Well, not so simple, but an application that I wrote earlier for desktop. And I want to run this on my custom Boot2Qt device. And for the most part, these devices, whether embedded Linux, embedded Android, it all works the same from Qt Creator. But to run on an arbitrary device, it's really just a matter of adding a kit. So if I remove this kit here, yeah, I have a selection of devices. It's kind of hard to see there, but I have a selection of devices that are for building the Boot2Qt stack. And in this case, I'm actually building for this Nexus 4, which is my custom device. If we actually look in the options at the kit settings, build and run, you can see here that what Creator has provided is, or what the deploy script has provided is a pre-configured kit. And the only thing that I actually have to do in this case is define what device I'm going to run on. So I use the device wizard to add a device here. Well, through this menu to add a Boot2Qt device that is an Android device over USB, and just selected that there. So if I add that Nexus 4 to my project, then I should be able to cross-compile for this device running Boot2Qt. So now, if you look down in the bottom corner here, you can see this little red dot here. This means that I'm not actually able to communicate with the device. So even if I was able to build the code, I couldn't deploy it to the device. But now if I hook up the USB cable to the device, and if Parallels behaves itself, then the light should turn green, and it does. And now building for this device should be as simple as just hitting run. So now it'll cross-compile for the device. It's deploying to the device, and shortly we should see, yeah. So maybe you can see, maybe it's hard to see in the back, but this is actually a Game Boy Color emulator, and now it's running on my Nexus 4, or former Nexus 4 phone that is running embedded Android. And we can, yes, thank you. And as I mentioned earlier, it's actually possible to debug this remotely. So I'm just going ahead and quickly set a breakpoint here. And instead of hitting run, I'm going to hit start debugging. And the same application should be restarted on this device. And the Creator's kind of got a weird resizing mode right now. But it's actually building, deploying. Oh, that's right. I have that messed up. I have to disable QML debugging right now. I'll try that again. Now it should actually connect quite quickly. So already I've hit the debug button. We're already running the application, and I can step through the application running on the remote device, just like you'd be able to on other platforms, just as easily as iOS or Android. We can do the same thing on embedded Linux and embedded Android. And you can see here I'm seeing the locals, I'm seeing the stack callback. All the things you'd expect from a debugging environment on the local host also working remotely. All right, so let's go back into this. And all right, so I just want to briefly mention some things that we're working on for the future, for the next release and the upcoming releases. You notice from the build steps for embedded Linux that it can be kind of complicated building things in two phases. We're actually moving everything to where it can be built, everything in Yocto. So there will be no separate phase between the Yocto phase and the building the Qt middleware layer phase. Instead, you'll do everything in Yocto, and you'll actually generate an image from Yocto that you can use with Qt Creator and its SDK directly there. The second thing is actually we're working on a low-end profile. So right now, all of the reference devices, all of the things we show, they are higher-end devices. They have GPUs. They run all of the demos we show. They run Qt 2. And they can be on the more expensive side of the embedded space. But you have to do a lot more work in the lower-end space. So what we'd actually like to provide is a low-end profile that will take advantage of 2D hardware acceleration like DirectFB. And then we announced this morning that we're looking into the Qt 2D renderer, We're actually using this to enable you to write the same Qt Quick 2 2.0 applications with Qt Enterprise embedded on these devices without GPUs. And the third thing that will be in the next release is Whalen multiprocess support. Right now, we're using Weston as the compositor where available. We know this is working on the IMX6 devices now, but this is something that will increase support for moving forward. There are varying levels of support because of the how good this doesn't always work the best as you'd expect it on all devices, and they're not powerful enough to actually provide 60 FPS and several different apps running at the same time. But we will have the option to take advantage of that. But okay, so that's actually it. That's all that I have for today. What I'd be interested in is your questions. So feel free to ask them now. And we have one question right here. Please wait for the microphone. Right?
Thanks to
yes.
Already for talk. Hello, test.
Yep, it's on.
Okay. So thank you. I have two questions. First, a yes and no question, and that is if the Qt meta layer image is based on Pokey.
It is.
It is?
Yes.
And the second one is, how come you're building Qt in a secondary step instead of using the Meta Qt 5 layer?
Okay. Originally, it was a difficulty, or if we're talking about the why aren't we building Qt in Yocto right now? It was because building the latest version of Qt was more challenging than it had to be using the Meta Qt 5 layer. So that's really the reason we've done that. We've since gone back, and that's what we're working on now, is actually modifying the Meta Qt 5 layer to work with our stack now. But originally it was because it was proving to be a barrier, and so to actually have something work as we intended, we did it the other way first.
Thank you. I also have two questions.
Okay.
And the first question also yes, no question. Do you have support for Bluetooth low energy?
We do, in the sense that in Qt 5.4, in the next release of Qt, the Bluetooth support that we have there does have support for Bluetooth low energy. So in the next release of Qt Enterprise Embedded, this will be true. And this is true because the Bluetooth layer on embedded Linux, libbluez, that's actually something that we provide as part of the platform layer. So you have a choice between BlueZ4, BlueZ5. Both of those work, and this will work with in the next release of Qt Enterprise Embedded.
Okay.
So there's actually a higher level API in Qt now to facilitate this.
Okay, thanks. And my second question is about licenses. Do you plan to have kind of a evaluation license or things like that?
Okay, yeah. So I should mention that now. We actually do provide we have an evaluation license available for this now. I know that there is a web page you can request interest in. I'm not entirely sure what that is, but I know that if you talk to the guys at the Qt Company booth or come get my business card later, I can definitely get back to you on the details of that. So there is an evaluation for that. I will mention though that by default the custom build scripts that I was talking about today, that's not currently part of the evaluation. So it's something you have to request. There's some questions in the back.
You talked about the emulation layer, and I wanted to know if it's a real emulation, sort of something like QEMU, or
so yeah. Regarding the emulator, so right now it is actually running. It's an x86, so it is a simulator in the same way that the iOS emulator is a simulator. Is it using x86? It is actually possible for us in the future to move this to a QEMU based thing, but it seems right now that it makes more sense to have it in this x86 based emulator. There is a OpenGL support for this as well, like hardware accelerated OpenGL support in our emulator. And I think there's a lightning talk about that later today, how that actually works.
Hi. So you just said that the Whalen support is ongoing, and my question is, when do you think it will be available, and if the Whalen support will be available in the open source version?
Okay, so the question is about the Whalen support. So in Qt 5.4, we actually are going to have support. This is including in all versions of Qt support for Whalen. So this is the Whalen client plugin and not the Qt Compositor API. Qt Compositor is still, this is the thing you actually implement compositors with, is still in tech preview phase. But the client-side API, this is I want to run a Qt application as a Whalen client to run in Weston. That is going to be fully supported with Qt 5.4 and is also something we're including in the next release of Qt, or Qt Enterprise Embedded.
Which options do you have for the development platform? As you said, you're fired up parallels.
Okay, yes. So we actually do have a requirement that to run our SDK, or the SDKs here, you actually have to be running Ubuntu, or not Ubuntu, but Linux 64-bit. This is because compilation becomes quite complicated when you're, say, building from Windows to the various devices. Because when we're actually generating the toolchains in Yocto, there are very few environments that actually support generating a toolchain that works from Windows. I think Intel's one of the cases where this is true, where it actually is supported. But for the most part, we can't actually get toolchains to work or generate toolchains in Windows to work in this way. But that's why it's the most fully supported. So in my case, I'm actually running a virtual machine of Linux 64-bit to run this stuff, and that actually works quite well.
My question would be, now all you showed us was basically the development environment. So how hard would it be to make the actual release version of my product then?
Okay, yeah, so that's where I think a lot of the improvements coming up with actually doing everything in Yocto will make that story a lot easier, the actual deployment image, because then you'll be able to generate the deployment image directly from Yocto, your final image. Right now, it would require a little bit of more manual intervention to generate that. So it's really just a modification of what your image target is, what things you want to include in your image, what user you're running as. So it's also a configuration issue.
One thing I wonder is that once you have your software stack written on top of Bootup, how easy is it to deploy that to multiple different hardware targets? How tied is it to the hardware?
Well, each individual, in the case of embedded Linux, it's actually dependent on the stack that you build. So if you're building an SDK for ARM v7, for this Freescale board, you're going to have a different SDK for this other board. I mean, you're going to generate an SDK for each device you actually have. In practice, or most of the time, this is just a matter of switching the machine target you build the Yocto layer for. So there isn't a lot of extra modification you have to do other than switching your machine target. But you will have a different kit for each device. It isn't like a, one universal thing to deploy to every device. Although it is an embedded Android case. It's per Android version.
Are there also runtime license fees?
This is subject to the distribution agreements with the embedded platform. So yes, the details we'd have to discuss with the representatives at the Qt company booth.
Any more questions?
Yep, I think that's good. Thank you very much. You've been great.